Hi everybody, this video is going to talk about graphing rational functions. Now, a rational function, as we've seen, is pretty much just like a fraction, but we want to get a little more specific here. So we're going to define a rational function as a function of the form f of x equals p of x over q of x. And the reason we write it like this will become a little clearer as we look at some of the rules on the next slide here. But it's important to know that p of x and q of x are both technically polynomials. So it could be a monomial, binomial, trinomial of really any degree in the numerator and the denominator. Another special rule here, and something that you really want to be careful of, is q of x cannot be equal to 0 because think of this as a fraction. Okay, we can't have 0 in the denominator of a fraction, so we can't have it in the denominator of a rational function either. So let's look at some of the steps that we need to go through in order to be able to graph. Okay, there are a lot of them. These are probably some of the trickiest types of functions that we've looked at as far as graphing goes, because there's a lot of key points and important pieces of information that we have to find that's related to the graph of that function. Now, first of all, you're always going to want to simplify the function. Now, that is pretty much what we've been doing up to this point. Okay, if there are some things that can be factored and canceled out, you should do that in order to simplify the function before you proceed. So after you have simplified, the first thing that we're going to look for is the x-intercept. And to find the x-intercept of the function, we're going to take the numerator, set it equal to 0, and then just solve for x. Okay, pretty easy. We're also going to have vertical and horizontal asymptotes that we look for each time. So some functions might have both, or they might just have one or the other. Okay, it really just depends. We're going to look at a lot of examples here, so you'll see how some have vertical, some have horizontal, sometimes they have one or the other. It just depends. So to find a vertical asymptote, we're going to be taking the denominator, setting it equal to 0, and solving for x. So very similar to finding the x-intercept. Notice here we aren't setting the numerator equal to 0, we're setting the denominator equal to 0 this time. And the reason we're doing that is we're really finding the x value that would make the denominator equal to 0, and we're going to make an asymptote there because we can't have our function basically living at that x value. So it's going to give us a boundary line because this function is going to be undefined at that particular value. Now, to find the horizontal asymptotes, it's a little trickier. We really have 3 cases, okay, and it's only going to be one of these cases. And it's looking at the degree of the numerator and the denominator. Now, remember, the degree of a polynomial is the largest exponent in that polynomial. So if the degree on top is bigger, then there is no horizontal asymptote. If the degree on top is smaller, then the horizontal asymptote is going to be right on the x-axis, which would be given by the equation y equals 0. The third case deals with when the polynomials have degrees that are the same. In that case, the horizontal asymptote is given by the equation y equals the leading coefficient of the numerator divided by the leading coefficient of the denominator. Now, remember that a leading coefficient, okay, let's just look at a quadratic equation, for example. Okay, quadratic functions in standard form would be like this. The leading coefficient is just the coefficient of the term with the largest exponent. So you're going to divide those values. It'll give you some number, and that's where your horizontal asymptote will be. Now, the 5th step is to find any holes in the function, and I want to elaborate as to what a hole is within this context. So a hole for a rational function is a point where there's actually a break in the graph. Okay, graphically, a lot of times it looks like this. So here's my y and x axis, and let's say my graph does something like this. Okay, and this is pretty common for rational functions for there to be multiple pieces. And as I go through this curve, there's actually a hole. There is a point that has been removed from that function. Okay, it's a point that makes the function undefined. Now, it's not just like a break in an asymptote. Okay, these are in addition to asymptotes. This point, a single point, has been removed from that curve. Okay, the points on either side continue in that pattern, but that point has been removed, and we show that just with an open circle like you see here. Now, this happens when there's a common factor in the numerator and denominator that cancels. So if you're simplifying a rational function and you notice that you cancel a common factor out, that's an indicator that you're going to have a hole for this function. Finding the hole is pretty straightforward. You just take that common factor that you find, set it equal to 0, and solve for x. To find the y value, you take the x value you just found, and you're going to plug it into that simplified function. The number that you get out after you simplify and use your order of operations is going to be the y value of the hole. So the hole is always going to be an ordered pair. So let's look at some actual examples here. So for our first one, okay, we've got x minus 4 over x plus 4, and we should try to simplify. Well, the numerator and denominator can't be factored, so this is already simplified. So I'm moving on to the next step, which is finding my x-intercept. To find the x-intercept, I take the numerator, I set it equal to 0, and I solve for x. So I'm going to find that x is equal to 4. So I'm going to go ahead and write that over here. My x-intercept is at 4, 0. And that point would be right there. Okay, next thing I'm looking for is my vertical asymptote. Okay, to find the vertical asymptote, remember that we take the denominator and we set it equal to 0. And then we solve for x. So we're going to find that x is equal to -4. Now, remember, a vertical asymptote is not a point, it is a vertical line. So when I write my vertical asymptote, it is the equation for a vertical line, which in this case is x equals -4. So we're going to make a dashed line through -4. And this is our vertical asymptote. Now, for the horizontal asymptotes, remember we have those 3 cases. For this example, the degree of the numerator is 1 because it's x to the first power, and the degree of the denominator is also 1. So we find the horizontal asymptote by dividing the leading coefficients. Well, this is a 1x over 1x, so the horizontal asymptote would be 1 over 1, which is just 1. Again, horizontal asymptote is a line, so you write it as the equation for a horizontal line. So we're going to sketch that in here. Now, the 5th step is to identify any holes in the function. Remember, there's only a hole if there was some common factor that we canceled out while we were simplifying. We didn't have that, so there is no hole. So we'll just put not applicable. Now, to get the rest of the graph, it's just like you would do for any other function. To get your other points, just plug in your function up here, look at your table, and plot the points that you find. Now, in this case, there's going to be a few nice points that we can plot. In general, I'm just going to do a rough sketch here. In general, our curve is going to look like this. But again, if I wanted to get specific points, I would just look in my calculator, look at that table, and I can pull them from there. So this is the general shape of my graph. Now, looking at it, I can now find my domain and range. The domain is going to be all real numbers except for that vertical asymptote, which was at -4. So to write that, we're just going to say it's all of the x values such that x does not equal -4. The range is also going to be written in the same kind of way, except we're dealing with y values now. And the only place that we can't have a y value is where the horizontal asymptote is. So all of the y values such that y cannot equal 1. And there we go. So for this next one, we're going to have some factoring that we can actually do. The denominator is a quadratic trinomial that would factor into x plus 5 over, or I'm sorry, not over, but times x plus 4. So I have a common factor. That is an indicator that there is going to be a whole. So keep that in mind for later. Okay, but let's keep going here. If I simplify this, this becomes just 1 over x plus 4. So now we can go through and find all that information. My x-intercept, I find by taking the numerator and setting it equal to 0. But in this case, in my numerator, I just have a number. So this isn't possible. 1 doesn't equal 0. That just means that we don't have an x-intercept. So we move on to find the vertical asymptote. We take that denominator in our simplified function, we set it equal to 0, and find that it's going to be at x equals -4. So then we can sketch that in here. So there's our vertical asymptote. And now we can look for, see how I make this go away here. Now we can go ahead and we can look for our horizontal asymptote. So remember, we have some rules. If the degree of the numerator is bigger, then we have no asymptote. If the degree of the numerator is smaller, it's at y equals 0. And if the degrees are the same, we get that horizontal asymptote by dividing the leading coefficients. Well, in this case, my numerator is a constant, meaning it has a degree of 0. The denominator has a degree of 1 because we have x to the first power. So this is case 2, where the numerator has a smaller degree, which means our horizontal asymptote is on the x-axis, which would be given by y equals 0. Now think about this, because we have an asymptote right on that x-axis, which explains why we don't have an x-intercept. Okay, that asymptote is serving as a boundary line. So if we have a boundary there, we're not able to have that x-intercept. Now the next step is the whole. And we said we were going to have one because we had that common factor of x plus 5 canceling out. So to find the whole, we just need to take that common factor that canceled out. Let's see, that was x plus 5. We want to set it equal to 0, solve for x. So we get x equals -5. Now that's just the x value of the whole. Remember, we have to also find the y value. And we find the y value by plugging it into the simplified version of that function. So f of x equals, well, I guess if we're evaluating, we should do f of -5 equals 1 over -5 plus 4. So that's really 1 over -1, which is -1. So our whole is located at -5, -1. So let's go ahead and put an open circle on the graph there. So -5, -1 would be right there. So there's the whole. And then if we go to our calculator and type this in, we're going to get our other points to make up our graph. So it's going to look something like this. Now, domain is not just going to be removing the vertical asymptote, because we have a whole here as well. We need to exclude the x value of the vertical asymptote and the x value of the whole. So x cannot equal -4 or -5. For the range, we have to exclude the y value where we have an asymptote, which is 0, and the y value of the whole, which is -1. And there we go. For this one, we have quite a bit of factoring that we have to do. Now, the numerator is one of those trickier ones to factor, so I'm just going to do it off to the side, well, actually down at the bottom here. If we have 2x squared minus x minus 1, we have to find two numbers that multiply to -2 and add to -1, because remember, we multiply the first and last together. So if we're thinking of these numbers, we can see that it's going to be a -2 and a +1. So now we are going to split that middle term and then factor by grouping. So factor out our GCFs. And our factored form is x minus 1 times 2x plus 1. So let's rewrite this up here. We really have x minus 1 times 2x plus 1. And in the denominator, this one's a lot easier to factor since the leading coefficient is 1. It's just going to be x minus 4 times x plus 3. Now, notice that a lot factored here, but nothing cancels, which is fine. We still need to factor to be able to more easily find the asymptotes and the x-intercepts. But notice that since there aren't any common factors, we can go ahead and say that there is not going to be a whole. So let's look at for the other information here. To find the x-intercept, we need to set the numerator equal to 0, but there are two factors in that numerator. So to find the x-intercept, we're going to set each factor equal to 0. Which means that we're going to have two x-intercepts. We're going to have one at +1, and the other is going to be at -1/2. So we can go ahead and plot those on our graph here. So let's see, +1, -1/2. So here and about here. All right, moving on. So vertical asymptotes. Now we're going to set the denominator equal to 0. Again, two factors. So we're going to set each of those equal to 0, which means we're going to have two vertical asymptotes. And I know that these are very easy to solve for. You don't have to go through all these steps. I'm just writing it out just since this is the first time you're seeing it. So we're going to have one at x equals 4 and x equals -3. So let's sketch both of those in here. And now we can go ahead and find that horizontal asymptote. Now, it's kind of hard to tell looking at our factored form here what the degrees are. So since nothing canceled, let's just look back to the original. We notice that we have a degree of 2 in the numerator and a degree of 2 in the denominator, which means this is case number 3. We're going to find that horizontal asymptote by dividing the leading coefficients. In this case, that's going to be 2 divided by 1. So horizontal asymptote is at y equals 2. So let's go ahead and sketch that in as well. Now, from here, let's go ahead and plug in our function into our graphing calculator and see what it looks like. You could type it in the original format, or you could type in the factored form, whatever you find easiest. And this one's going to be a little different because there's actually 3 parts to the graph. The first part is up here in the upper left-hand corner. Then we have a middle part that is a parabola. And then on the right side, we have another curve up in the upper right-hand corner. So here's our graph. Domain and range is going to be a little trickier here. We have 2 vertical asymptotes. We have a horizontal asymptote. The other thing to notice is that the maximum on our parabola here in the middle, it doesn't go all the way up. Like, it doesn't get very close to that asymptote. So what I'm going to do is I'm going to look at my graphing calculator, and I'm going to calculate the maximum of that little parabola piece. And it says that it is at 0.24, 0.09. So this y value is going to come to play in my range in addition to that horizontal asymptote. So let's write it out here. The domain is going to be all of the x's such that x cannot equal -3 or +4. Okay, those were where my vertical asymptotes were. The range is going to be everything greater than my asymptote and everything less than that highest value on my little parabola piece there in the middle. So my range is all of the y values greater than 2 or less than or equal to, since it's that maximum, 0.09. So that's a complicated one because of that middle piece. It kind of makes things tricky. All right, another one where there's quite a bit of factoring, but pretty easily done. In our numerator, this is going to factor into x plus 7 times x minus 4. The denominator is going to factor into x plus 7 times x plus 5. Now notice that we do have a common factor here of x plus 7. So we're going to cancel this out, and that tells us that there's going to be a whole for this function. So our simplified function is going to just be x minus 4 over x plus 5. So from here we can find the x-intercept. If we set that numerator equal to 0, we're going to find that we have an x-intercept at 4. To find the vertical asymptote, we set the denominator equal to 0 and find that we have a vertical asymptote at -5. For the horizontal asymptote, since the numerator and denominator have the same degree of 1, we divide the leading coefficients, which are both 1, and find that we have a horizontal asymptote at 1. And now we have to find the whole. So we're going to take that factor that canceled, which was x plus 7, set it equal to 0, solve for x. So the whole has an x value of -7. To find the y value, we're going to plug this into our simplified function. So f of -7 would be -7 minus 4 over -7 plus 5. So that's going to give us -11 over -2, which is just +11 halves, which is 5.5. So our whole here is at -7, 11 halves. So let's get these asymptotes and x-intercept and the whole plotted, and then we can get the rest of our points. So let's see here. Our horizontal asymptote is at 1. Our vertical asymptote is at -5. We have an x-intercept at 4. And we have a hole at -7, 11 halves, which is about 5.5. So 5.5 would be about here. So we'll put an open circle there. Okay, now, if we look at our calculator, we can get the rest of our points, and our graph is going to look something like this. So there we go. Now, domain and range. Because there is a hole, in addition to these asymptotes, there are going to be multiple values we need to exclude. Okay, the domain should be all of the x values except the x value of the vertical asymptote and the x value of the hole. The range should be all of the y values except the y value of the horizontal asymptote and the y value of the hole. So there we go. So we're going to look at one more example. Okay, so let's start by factoring and simplifying here. The numerator is going to factor into x minus 5. Oops. Times x plus 1. And the denominator has a GCF of 2 that can be factored out, which reveals a common factor of x plus 1 that's going to cancel. So again, that means that our function is going to have a hole. So the simplified function is x minus 5 over 2. Now, I'm going to rewrite this a little differently so that it looks like 1/2 x minus 5 halves, because this is really going to look, if you type this in and graph it, it's going to look like a straight line. So this is going to help us graph a little more easily. But before we go ahead, let's just focus on the simplified function without dividing by the 2 and find our key information here. Our x-intercept we find by setting the numerator equal to 0. So that's going to give us a positive 5. The vertical asymptote we find by setting the denominator equal to 0, but since the denominator is just a number, there is no horizontal asymptote because there is no x value to solve for. There is no x value that's going to make that denominator in the simplified function equal to 0. So there is no there is no vertical asymptote. Now, the horizontal asymptote, this is going to fall under case 1, where the degree of the numerator is bigger than the degree of the denominator. Okay, the degree of the numerator is 1 because it's x to the first power. The degree of the denominator is 0 because there is no variable. So that means that there is also no horizontal asymptote. So now we need to find the hole. We're going to take that common factor that canceled out. So what was it? X plus 1. So the x value of the hole is at -1, and to find the y value, we just plug it back into our simplified function. So that's going to give us -6 over 2, which is -3. So now we can say that the hole is at -1, -3. So let's plot the hole. Let's plot our x-intercept. And then let's use this form of the function to graph it more easily. Okay, I already have some points labeled, so I could use my slope of 1/2 to just get from one point to the next. Or you could plot your y-intercept of -2.5. and do the same thing. Now, if you do that, you're going to get something that looks like this. So this is an example where we didn't have any asymptotes. There was a hole, but there were no asymptotes. So our function isn't broken into multiple parts because of that. So it's okay to have something that looks like this. It comes up every once in a while. So because there are no asymptotes, the domain and range are only going to take into account the values of the hole when we're excluding. So domain is all of the x's except -1. And then the range is all of the y's except -3. All right, guys, I know this was a long video, but there was a lot of information to cover. Don't hesitate to reach out and ask me questions. I know that some of this is pretty tricky. Just keep practicing. Let me know if you have any trouble, and have a great day.